Hi, so today we'll look into strong acid versus weak base. In the beginning, let's assume we have NH3 as our weak base. So because the graph is starting at a higher point than 7, I know that my initial stage, I have base. Now I'll write down the equation for this. I'll dissociate it into water. This will make this is NH3. H4 plus OH negative. Then I move on to my neutralization, which is step 2. I have my base, I have my acid, and this results in NH4 plus H2O. Now over here, you need to know that this reaction goes to 100% completion. If you notice over here, this partially dissociates. The reason it partially dissociates is because NH3 is a weak base. However, at neutralization, it goes to 100% completion because I'm reacting with the strong acid. And because I have a strong acid, so I just need to use the H3O positive ion. So let's say I have HCl. So because it goes into 100% completion, I can just straight up use this. And these two are interchangeable. Yeah. Now I move on to my step 3, which is my equivalence point. At equivalence point, moles of acid equals moles of base. Here, I'll use the products of my previous step as my reactants here. So NH4 plus H2O would give me NH3 plus OH. H3 positive. Now because over here I'm producing H3O positive, this would mean that when I find the pH at this point, my pH would lower down. So lower pH would mean that my solution is acidic. Does that make sense, or does that not make sense? It does make sense because I have a strong acid. Because of the strong acid, if I keep on adding more acid, so that would result in a acidic pH. That's why over here, if you look at the graph, this graph goes here, so because this refers to the fact that my pH is going to become more acidic. So over here, what I'd quickly like to add is that because we have a strong acid versus weak base, at neutralization we have a buffer. Even if it were the other way around, so let's say it was strong base versus weak acid, we still would have a buffer at neutralization. So this means that if I were to find pH at neutralization stage, I would use my Henderson equation, which is this concentration of base divided by concentration of acid. Yeah, so this would mean that in order to find the concentrations for weak and for base and acid, I need to use my stoichiometry. So that means that I'll find the limiting reagent. Well, for starters, I'll find the initial concentrations. Then I'll find the limiting reagent. Then I'll find the number of moles left to me, and then I'll just plug the values in and find my pH. Today we'll look at this question and try solving it. It says NH3 and being titrated with HCl, so it's our strong acid versus weak base titration. So in the beginning, all that I have is my base. I'll write down the equation for that. H2O dissociates into NH2. Now because it says pH, I'll write down the formula for pH to give me a sense of what it is that I need. Now, I need the concentration for H2 positive ions, but I don't have any concentration for H2 positive ions. So for that, in order to get to this point, I'll need to find the concentrations regardless. But now you might see that I'm given concentrations here, but why can't I just, if I need to make an isolate, why do I need to make an isolate? But why can't I just use the concentrations provided to me? Well, that's because these concentrations are the initial concentrations. What I need are the concentrations at equilibrium. And the equilibrium concentrations are the concentrations that you plug in here. So initial concentration for NH3 is 1 molar, and this would be 0, 0. Change is negative x, positive x, minus x. Now for water, you just cross it out because that means how much concentration of water do you have in water. That doesn't make sense, so you just cross it out. It's infinite anyway, so that's how you just cross it out. Now also I put a negative over here because my reactant is getting consumed and my products are being made, so I put a positive over there. And then it's negative 1, 1, 1 here because I have 1 moles of all of these things. The molar ratio is 1 to 1 to 1. Now I'll plug my Kb here. Now why am I plugging my Kb here? Why am I not talking about Ka? Well, that's because I'm producing OH negative. That's why I know that I need to plug my Kb here. Minus x. Now because the value for Kb is given to us, I'll plug that in. Now over here I can use my small x approximation. I can do that because whenever your K value is anything 10 to the power negative 5 or lower than that, you can use the small x approximation. So this would equal to, and then the value for x is going to be equal to 0.0013. Now from here, you have the value of x. This means you have the concentration of OH negative at equilibrium. Now there are two things that you can do from here. Either you use the formula Kw, concentration of H2 positive, OH negative, method 1, and then plug the values in. 0.0013 equals concentration. This would equal 7.6923 times 10 raised to the power negative 12. pH equals minus log H3 positive. So pH here, when you plug this value in, the pH would be 11.11. Either you could do this or you could do method 2, which is you have the concentration for OH, so rather than finding the pH, you can find POH. The formula is similar to that of OH for hydrogen. So OH here, so negative log of 0.0013 gives POH, which is 2.88. Now from here, you know that pH, the scale of pH is up to 14. So this is equal to, pH is equal to P of OH plus P, sorry. You get this? Now you can say pH plus POH equals 14 and pH would equal 11.11. That's it. So now we'll look at part B of this question and try solving it. Because it says after addition of 20 ml of 0.1 molar HCl, that means we're adding HCl, we're adding acid to our base, so that means this is neutralization stage. And I'll write down my equation here. This goes to NH4 positive plus H2O. Now this reaction is 100%, it goes to 100% completion because we have a strong acid over here. Also, I didn't break my NH3 down into ions. However, I broke my HCl down into, I dissociated it because HCl is a strong acid, it completely dissociates. So I can just write, so H plus is interchangeable with H3O positive, so I can just use this over here rather than using HCl. But I can't do the same for NH3 because NH3 is a weak base. Now at neutralization, we have to find the pH, I'll use the Henderson equation over here to find the pH. Log base divided by log of concentration of acid. So the reason why I'm using Henderson equation over here is because we have a buffer available to us. How do we have a buffer available to us? Well, there's a buffer because we have a weak base and also its conjugate acid. So weak base alongside conjugate acid. So that is one way to make a buffer. There are two more. There's another way to make a buffer. That let's say I had my weak base, alongside it I had a salt of my weak base. So let's say I had NH4Cl. So this is ammonium chloride. So presence of this would also make a buffer. Either you have a weak base along with its conjugate acid, or you have a weak base along with its salt. And same goes for acid. So let's say you have a weak acid along with conjugate base, or you have an acid along with conjugate along with its salt. But that's what you usually see in weak acid versus strong base. So over here it's the other way around. Okay, so now I need to put in pKa value here. So pK, how do I find pKa? Well, they gave me my Kb, so I can use my Kb. So that would be Kw equals Kb times Ka. I have this, I need to find this. So, and the value for Kw is a constant, so you always have it. I think it's 1.8, yeah. So Ka would equal 5.5, 10 is over negative 10. So now we find pKa, which would be pKa equals negative log Ka. So you plug this value in here. This is Ka. So this gives you 9.255. So I'll write pH equals 9.255 plus log. Now I need the concentration for my base and my acid. How do I find them? Can I use the concentration that is provided to me here, like 0.1 molar HCl and then 1 moles of NH3 that are available to me? No, I can't use those concentrations, because your buffer got created when you mixed those two things up. You mixed your HCl with your base. So you can't put these concentrations here, because these are the initial concentrations that you had. But in order to find these concentrations, you need to find the number of moles that are available to you. So I'll find the number of moles for HCl, that is concentration times volume. So 0.1 times 20 divided by 1000, this would give me 0.002 moles. I'll do the same for NH3. So concentration is 1 molar times 40 divided by 1000. This would give me 0.004 mole. I got this information from here. Anyways, now that I have my moles, I need to find my limiting reagent. Now my limiting reagent would be my HCl, because it has lower number of moles. So NH3 would be a limiting reagent in comparison to H3O positive would be a limiting reagent in comparison to NH3. So now that means that I need to find the number of moles left behind for NH3. So how will I do that? Left moles would be the moles that I had available to me subtracted with the number of moles that got consumed, gives me the moles that were left, which is 0.002 moles. So this is the amount of moles that I have left for NH3. Now you found the initial concentration. Now remember, concentration, it changes, however your moles, they stay the same. So that means that once I add these two things up, when I add my HCl to my NH3, the volume is going to change, because you have 20 mLs of HCl, you have 40 mLs of your NH3. So your total volume now would be 60 mLs. Using that information, you're going to find the moles that are available to you in these two places, that are the concentration that is available to you in these two places. Because your moles stay the same, I can just use the same number of moles that I had for NH3, which are the leftover moles, which are 0.02. So number of moles of NH3, this is the leftover, concentration times volume. So the number of moles that I have are 0.002 divided by 60 divided by 1000, because I need to change it into liters. I'll get the concentration, which would be 0.0033, I guess. Yeah, so I added the volume up because this volume 60, I get 60 volume because I added my NH3, which was 40, into my HCl, which is I added my HCl to my base, so 20 to my 40. That's how I get my 60. So now, because NH3 is in 1-to-1 molar ratio with NH4, I know if I'm producing 0.03 moles of NH3, I'm also producing 0.03 moles for NH4 positive. So this is so this would mean that NH3 ratio NH4 positive is 1-to-1. So if I'm producing, if I have the concentration of 0.003 for NH3 molars, I also have it for my NH4 positive. So over here, also know, you need to know, like, your base over here is your NH3 and your conjugate acid is your NH4. That's why I'm always like, that's why I mention like NH3 versus NH4, because NH4 is your conjugate acid over here. So I'll put the concentrations in here. 0.033. So because this is what I got here, right? So I plugged those values in here. So because because these two are the same quantity, so log of let's say 1 divided by 1, or 0.033 divided by 0.033, this would give me 1. So pH, sorry, it would give me 0. So 9.255 is my